detecting exotic Four manifolds. Take it away.
Thanks very much for the invitation, for this chance to speak here in the Congress. So today I'm going to talk about this Lasagna s-invariant detecting exotic Four manifolds. This is based on joint work with Mike Vonis. So let's get started. So here on my screen, you can see two knots. The first one being the mirror image of the 5-2 knot in the Robson table. And the second one is a certain Fresnel knot, P3, -3, -8. And I have those small -1 framing coefficients written on top of those two knots, which suggests that I am really drawing Kirby diagrams of Four manifolds. So for the first diagram, for example, this is the so-called -1 trace on the 5-2 mirror knot. -1 trace. On 5-2 mirror, and it's obtained by, I start with the 4-ball, and then well, my knot sits in the boundary S3 of this 4-ball, and I can attach a 4-dimensional 2-handle along this knot on the boundary. 2-handle along 5-2 in boundary with a certain framing -1 relative to the cipher framing. So this gives us a Four manifold, a compact orientable Four manifold simply connected, called the -1 trace on my knot. And similarly, for the second picture, I get the -1 trace on P3, -3, -8. So the main theorem of today's talk, let me write this down, is that those two Four manifolds are exotic. So in Four manifold topology, when we say a pair of manifolds is exotic, this means that they are homeomorphic. But not diffeomorphic. So the purpose of today's talk is to introduce a certain invariant coming from the so-called skin lasagna modules that enable us to distinguish the smooth structures on those two Four manifolds. But before doing that, I must first make a remark, which is that this pair of example was not originally due to us. This theorem in particular, it was first proved by Bunut in 91. And the way he showed that those Four manifolds are homeomorphic is via a sequence of Kirby moves to show that, well, at least the boundary of those Four manifolds are homeomorphic. And then, in fact, this plus the framing condition, the framing agree is already sufficient to imply using some deep theorem of Friedman, deep result of Friedman shows that those Four manifolds are homeomorphic. So by now, I think this homeomorphic part of the statement is kind of one can say standard if you are willing to assume this deep black box by Friedman. However, the other part of the statement that the two full manifolds are not diffeomorphic, this is often the more interesting part. And Bunut was able to show this by a very intricate calculation of the so-called Donaldson invariants. And he was able to show that those two full manifolds have different Donaldson invariants, which are invariants defined for smooth manifolds. And the manifolds having different smooth Donaldson invariants imply that they are not diffeomorphic. And later, there are easier proof of the same result again, I think by Bunut and one of his collaborators using the Seiberg-Witten invariants instead of the Donaldson invariant. And the calculation formally is simpler, but still that depends on many deep results in, for example, symplectic geometry. But today, what we are going to do is to provide so-called analysis free proof, and I'll explain what our invariant is for us to accomplish this task. And as far as I know, this is the first gauge theory free proof of the existence of exotic compact orientable full manifolds. Okay, so let me begin the talk by briefly introduce the so-called skin Lasagna modules. This was a package of invariants defined by Morrison, Hawker, Weldrick in a recent paper. And well, the input for skin Lasagna modules is the so-called Koanov homology, which I will denote by KHR2. Formally, this is just a functor from the category of links in S3 to the category of vector spaces, maybe with some extra grading structures, which I'm going to ignore for the moment. This is a so-called Koanov homology. And then the skin Lasagna module is a package that formally takes in a TQFT-like functor, like Koanov homology, and then upgrade it to a certain full manifold invariant, denoted by this script sub-0 upper 2 x, where x is a compact oriented full manifold. This is the so-called Koanov skin Lasagna module. I'll just sketch a brief definition of this invariant, but our main talk will not really go deep enough to make use of the actual definition. So I just want to give you a feeling how this invariant is defined. So as a vector space, this skin Lasagna module of X is generated by some formal pictures like this. So this is my full manifold X. It may have some boundary. And I'm going to consider surfaces in this full manifold, which I will call skins. but not exactly in the four manifold, but rather in the four manifold with finitely many four balls deleted. For example, here I'm deleting two little four balls out of my four manifold X, and then I'm going to consider an embedded surface in the complement of this those four balls, something like this. And those surfaces will come with some extra decorations. So the surface may have some boundaries in the four balls that on the boundary of the four balls that I deleted, and the boundary of the surfaces on each boundary S3 is a link. So we get a bunch of links L1, L2, etc. And those links comes with some extra decoration, V1, V2, etc., where Vi is a label, is an element in the Kohanov homology of my link. So I take all formal pictures like this of the formal skins with coming with Kohanov decorations. This seems a crazy thing to consider. I take the Q linear span of all those things, but I'm also going to mod out some relations where the relation includes, well, first of all, I can freely isotope my surface, my skin, as well as my input balls, the small b4. And that should not affect the element this object represent in the skin Lasagna module. And secondly, we need to module the linearity in the labels. I guess more precisely multilinearity. So really, this V1, V2 label, you should really think of them as a total decoration by V1 tensor V2. So if you have two decorated skins where the underlying skins agree, but maybe they have different labels, you can formally add those labels up together in a multilinear way. And there's a third relation, which is the most interesting, which I call the enclosement relation. This is the following picture. So if in some local picture, I see a number of small balls and a part of my skin, say like this. And suppose that I can enclose a certain local picture by a slightly larger ball. Then I'm allowed to just delete everything inside this larger ball and declare that my previous element given by this skin is equivalent to the later element where I delete everything inside. But of course, we also need to keep track of the labels. So if we have label V1, V2 for links L1, L2 inside, then we need to upgrade them to a certain label V for the outside link L. And that is that piece of data is given by just the structure of the Kohanov homology, because the part of my surface between this red ball and the two blue balls provides me a coborizon between L1 disjoint union L2 to L, and the functoriality of Kohanov homology provides me this upgrade. So this, the left-hand side is the same as Kohanov L1 tensor Kohanov L2. So my label gets updated in this way. Anyway, after doing such formal this formal definition, we obtain an invariant for smooth four manifolds. And well, in fact, we don't need too much about our input homology being the Kohanov homology. We could have do the same for any TQFT with similar structure. For example, there is a certain deformation of the Kohanov homology, which I will use today, called the Lie homology, denoted by KHR sub Lie. It formally has the same structure as Kohanov homology. So I'll just change the notations involved in my notes by changing these two everywhere to Lie. So my labels now becomes elements of the Lie homology, and everything else just stay the same. You run through the same definition, you get this the invariant called Lie skin Lasagna module. And if you are familiar with the classical story of Kohanov homology and Lie homology, you should know, for example, that the Lie homology KHRD has actual grading and filtration structures. So it has an edge grading. This is the so-called homological grading, and there is a filtration labeled by Q. This is the Q stands for quantum. H stands for homological. And those structures will be preserved in this Lie skin Lasagna module. So parallelly, Lie skin Lasagna module of a four manifold has again, it has the H grading, it has the Q filtration, but it gets one more piece of grade data, which is what I'll call an alpha grading, where alpha is nothing but the homology class of my skin inside this picture inside used to define an element in the skin Lasagna module. And you can easily check that the homology class is well defined because the four balls are too small to see the second homology class, and that all the three relations will not change this homology class of my skin. So this Lie skin Lasagna module is graded by a homological degree Z, and by an alpha degree H2 in H2 of my four manifold, and there is a Z filtration by Q. So again, if you know the classical story, you might know that the homology of a link is in some sense boring, because we can, as a vector space at least, we can just explicitly write down what it is in terms of some very stupid algebraic data of my link L. And parallelly, there is the so-called structure theorem. Of these Lasagna modules, saying that exactly the same thing happens for the skin Lasagna modules of a four manifold. You can write down as a vector space at least what it is. So as a vector space, the least-skin Lasagna module of a full manifold is generated by a pair of second homology classes over Q. More explicitly, it's a Q vector space generated by some formal variables x alpha plus, comma alpha minus, where alpha plus and minus are both second homology classes of my full manifold. So this is an isomorphism as vector spaces. Maybe I should say this isomorphism is canonical. So if you ignore the further structures of this skin lasagna module, then it seems that we have created a somewhat boring invariant. But just like in the classical case, this skin lasagna module is indeed interesting if one consider the Q filtration on this particular vector space. So I'm going to define the so-called Lasagna s-invariant as follows. The Lasagna s-invariant of X at a certain homology class alpha, second homology class, it is denoted by S, X semicolon alpha, which is defined by the quantum filtration degree of a certain generator in my least-skin Lasagna module. This generator is this X alpha sub 0. So this Q is the quantum filtration function on my least-skin Lasagna module. And a caveat is that this filtration function might send non-zero element to negative infinity. As a consequence, the Lasagna s-invariant values in Z, but possibly also negative infinity. And as a matter of fact, when the Lasagna s-invariant is negative infinity, we will call that, we will regard this as a vanishing result for s-invariant. Okay, any questions at this point? I guess I haven't said anything with real essence, but now I'm going to list some formal properties enjoyed by this Lasagna s-invariant. So I call them properties because they are not particularly deep. If you trace through this canonical isomorphism in the structure theorem and how everything is set up, then those properties will more or less be some easy formal consequences. The first property I want to talk about is the additivity. So this says that if you have two different full manifold x1 and x2, and you take the connect sum of them, then if you specify a second homology class to be alpha 1 comma alpha 2, where alpha I is a second homology class of xi, then the s-invariant of this class is probably as you expect. It's just the sum of the alpha 1 class of x1 and alpha 2 class of x2. And if your full manifolds have boundary, you can also replace this connected sum here with boundary sum. And you can always just trivially replace this connect sum with disjoint union, and the same formula will hold. The second property I'll call monotonicity is the following. So if I have an embedding between two Four manifolds from x1 to x2, then this Lasagna s-invariant is kind of monotone under this embedding, in the sense that the invariant of a class alpha of x1 is greater or equal than the corresponding class in x2 obtained by just push forward. So in principle, this gives you some sort of obstruction between embeddings of Four manifolds if you do their Lasagna S invariants well enough. And the third property is called the genus bound. This is a bit reminiscent of the adjunction inequality obtained in cyber-Witten theory and maybe some other gauge theory. So if we let G x denote the smooth genus function of a Four manifold X, formally this means the minimal genus of a smoothly embedded surface that represent my given second homology class alpha. This is the so-called smooth genus function of X. Then we get a lower bound of this genus function from the Lasagna S invariant of the Four manifold. More precisely, the genus function at a class alpha is bounded below by S invariant at alpha plus the self-intersection number of alpha divided by 2. This is the self-intersection number. Okay, so those are nice. But then I also want to present some deeper results, which I will call theorems of the Lasagna S invariant. And hopefully I will be able to do some examples along the way. So the first big theorem we proved in our paper, which I'll call theorem V. There V stands for vanishing, states the following. If a certain knot trace, the n trace of K embeds in X for some knot K and integer n, recall the n trace is the Four manifold obtained by attaching a two handle along K in the boundary of B4 with framing given by n. Suppose that this pair Kn satisfies that n is large enough in the sense that it is larger than a certain numerical invariant of K called the maximal TB number. I guess n is greater or equal than the maximal TB number of the mirror image of K. Then the existence of this elementary piece, this knot trace inside my larger Four manifold, just kills all the Lasagna S invariants of my larger manifold X, in the sense that all the S invariants are are negative infinity. So let's do an example here. So in this vanishing theorem, let's take K to be the unknown. The maximal TP number of the unknown turns out to be -1. And what is the n trace on the unknown? Well, this is nothing but the D2 bundle over S2 with owner number n. But in the four manifold context, you can also realize this manifold as a turbulent neighborhood of a smoothly embedded two-sphere inside a four manifold with self-intersection n. So what does theorem V says in this case? Well, it exactly says that if you unwind the statement that if my four manifold X contains a positive two-sphere, meaning an smoothly embedded two-sphere with positive self-intersection, then all the Lasagna s-invariants of X are negative infinity. Okay. Well, in particular, I guess we know many interesting four manifolds with a positive two-sphere like this. For example, X can be CP2. The core CP1 is a two-sphere with self-intersection 1. And for example, we have X2 times S2, because if you take the horizontal S2 and the vertical S2, and tube them up appropriately, you will get a two-sphere with self-intersection 2. And you can also take the K3 surface, but with the orientation reversed. That also turns out to have a positive two-sphere with self-intersection 2. So theorem V implies that all those manifolds will have vanishing Lasagna s-invariants. Okay, but for the purpose of proving our mean theorem, we will need some non-vanishing results. And I'll list two particular non-vanishing results. The first one, theorem N1, says that if I have a knot in S3, that is a positive knot. Meaning that it admits a diagram where all the crossings are positive crossings. For example, if we go back to our pair of knots, then this first knot, 5,2 Miro, is a positive knot because you can check in this particular diagram that all the crossings are positive crossings. This theorem says that whenever we have a positive knot and a non-positive framing n, then the Lasagna s-invariant of the n trace on K at class 1. Here 1 is a certain class in H2 of this four manifold, but this four manifold has H2 isomorphic to Z, and by writing 1, I'm just picking a generator of this Z. It doesn't matter which one I pick, there are two choices. But anyway, this s-invariant will turn out to be equal to the Rasmussen s-invariant of my knot K minus n. This S is the classical Rasmussen s-invariant. And we'll need a second non-vanishing theorem, theorem N2, which says that if K is a Snides knot, a Snides knot means that if you put a knot on the boundary of B4, then we can find an embedded 2 disk in the interior of B4 with boundary exactly being the given knot K. So for example, if we go back again to our pair of knots, this second knot P3 negative 3 negative 8 turns out to be a Snides knot because I guess you can almost see a Snides disk in this picture. So the disk, part of the disk is like this, and it twists along with the bands, and it goes back to close up. Unfortunately, if we just draw this disk in S3, it will have a self-intersection being a certain segment. But if we have the fourth dimension, we can push one of the layer along those intersections slightly below the other layer in the fourth dimension, which I indicated by drawing the two sheets in different colors. So this is, if you have the fourth dimension, you can find such a disk. Without self-intersection, this manifests the fact that the knot P 3 negative 3 negative 8 is a Snides knot. The second theorem says that whenever we have a Snides knot and again a non-positive framing, then the s-invariant of the the n trace on K again at +1 is simply negative n. Well, I guess maybe I could have stated the two theorems together because a Snides knot always have Rasmussen s-invariant 0. So I could have said that if a knot is either a positive knot or a Snides knot, then the same formula above applies. I guess this formula in green applies to both cases. But anyway, those two theorems are proved somewhat differently, so I prefer to state them separately. So I think I'm formally allowed to only speak for 40 minutes, so I'll try to finish up by giving you a proof of the mean theorem using the facts that I have stated. Proof of the mean theorem, which states that, well, I guess, which states that this pair of knot traces are exotic, but I guess we will only prove the non-diffeomorphic part, which is the interesting part. Only prove those two manifolds are not diffeom. Well, actually, so this is now very straightforward application of what I told you, because by theorem N1 applying to the 5-2 mirror knot, we know that the Lasagna s-invariant of the first four manifold at class 1 is equal to the s-invariant of this 5-2 mirror minus the framing, which is -1, and the Rasmussen s-invariant of 5-2 mirror turns out to be +2. So this is 2 + 1, which is 3. While on the other hand, theorem N2 tells us that the same thing for the second manifold is simply negative the framing, which is +1, and those two s-invariants are different. Well, what does that mean? Well, if we had a diffeomorphism between those two four manifolds, then they will necessarily it will necessarily carry this this one class in the second homology to another class which I call one, and in the other four manifold. But the Lasagna S invariance, as we define, was supposed to be a smooth four manifold invariant. So those two numbers being different just tells you that they are not diffeomorphic. So this is the proof. And I think I can quickly give you a second proof of the same result using something else I said. Alternative proof. So by this genus bound result, maybe I'll copy this formula down here. By this genus bound, we know the genus function of my first four manifold, the trace on the 5-2 knot at class 1 is greater or equal than we have calculated the S invariant by theorem N1 to be 3, and plus the self-intersection of this negative 1 class, of this 1 class divided by 2. So this notation is a bit misleading. The second term is really the self-intersection number. So it's actually -1 instead of +1. So this right-hand side turns out to be 1, which means that I cannot represent a primitive class in this four manifold by a smoothly embedded two-sphere. But on the other hand, this second knot P3, -3, -8 is nice. This implies that class 1 in the second manifold can actually be represented, by a two-sphere. Namely, if you take the slice disk and you cap it off by the core of the two handle you are attaching, then that gives you a smoothly embedded two-sphere representing by primitive class 1. So that means, well, this gives you a more geometric proof of those two four manifolds being non-diffeomorphic. So I guess I'll stop here.
Yes, thank you.